Hey everyone, in this video let's take a look at question 33, search in rotated sorted array on Leetcode. This is part of our blind 75 list of questions, so let's begin. In this question, there is an integer array num sorted in ascending order with distinct values, and prior to being passed into the function, the nums is possibly rotated at an unknown pivot index. For example, this question is actually very similar to the one we did before, find minimum in rotated sorted array. But essentially what we have is we have an array, maybe it's 1, 2, 3, 4, 5, 6. Initially, it is sorted, but what we get passed in is a rotated array. So maybe this has been rotated 2 times, so we can have something like 5, 6, 1, 2, 3, 4. So essentially, we have this value here, this array here. In this question here, find minimum, we're basically asked to find the minimum, and we did that using binary search. In this question, we're here to find basically any value that's being passed in, essentially the target. So we're passed in this array here, which is sorted, and it has been rotated after, so it's not sorted anymore, but it has been rotated, and we're asked to find the target. And we want to do this in O of log n time. So again, we want to use binary search here. So basically, I'm not going to go through these examples that we have over here because they're pretty self-explanatory. They don't really tell us how to do anything, so it's not really that important here. But whenever you see this log n type algorithm, then you want to kind of think of binary search. And I don't want to dive too deep into kind of the thought process behind this question because it actually follows a lot from this find minimum and rotated sorted array. So definitely watch that one. But I will try to kind of present the main idea of this question. And in order for us to do that, let's just kind of take a look at this thing that I have here. This I basically figured out, or I basically drew out in the last question that we did. And so I'll basically just go ahead and summarize what I have here. So we have a couple of cases, right? In the first case, we can have the case where array is not sorted at all, or maybe it's been rotated like n number of times, or n is the size of the array. So we're back at where we were initially. So in this case, we notice that the array is strictly increasing, right? It's strictly increasing. Maybe the array has been sorted, and then it has been rotated some amount of time, such that we have something like this. In this scenario, what do we have? Well, we have a single peak, and then we go down, and then we go up. So you can kind of think of this as we increase, we increase, we increase, we decrease, and then we increase, we increase, we increase again. So that's what this means. We increase all the way up here, and then we decrease back to the 1, and then we increase. So essentially, we have something like this. We have increase, 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 decrease, and then increase and increase and increase. And what we kind of reasoned through this was that basically after we decrease, well, we know this decrease element here is our minimum, is our pivot, but basically after we decrease, whatever we increase after that, it cannot have been greater than the left-hand side, right? So it cannot actually surpass this peak that we have over here. And it's kind of very easy to see this. For example, if we have the array just 1, 2, 3, 4, 5, right? Then initially this is just one giant leap in the forward direction upwards, right? So it'll be something like this. But for example, if we go about rotating this array, so let's say we have something like now 4, 5, 1, 2, 3. Well, now what we will have is we'll have something like this. We'll have 4 and then 5. So 4 and then 5. And then 1 will go all the way down here. And then 2 and 3 will go up. But essentially note that this 2 and 3, this array on the right-hand side, it cannot be greater than our peak over here. It cannot be greater than the peak. So basically, I'm just summarized over here. You can essentially think of this as the dip can only occur once, right? So we can only have like one dip in the array. And whenever that dip does happen, then we know that we are at a minimum, right? So that's what we did on the left-hand side. And so we can also notice here that the left-hand side is always greater than the right-hand side unless the array is already sorted. So you can also notice here that the left-hand side of the array, this side here, it will always be greater than the right-hand side, right? It will always be greater than the right-hand side. So this 4 here will always be less than this left-hand side here, unless the array is like already sorted. Because when we sort, then we add it in a dip, right? So when we sort, it's like we have something like this, but instead we add in a dip, right? We add in a dip. So then the right-hand side is actually going to be lower than the left-hand side. But in that case, like we don't need to really worry about that here. Okay, so how might we go about doing this question, right? So we already did this I'm not going to explain too much about this question because we already did this a lot in the find minimum question. But if you really think about this, let's go back here, right? So we already made the observation that what is our observation? We have a single dip, but on the left and right hand side of the dip, we are increasing, right? We are increasing. And another observation we can make is, so here is the dip, right? So here is the dip over here. Basically, if you think about the dip, right? If you include the dip in one of the sides, then that side will be entirely increasing. And then on the other side will essentially be increasing and then will decrease at one point. So there will always be one side that is entirely increasing. There will always be one half that is entirely increasing, right? The other half will contain the dip. And so it will increase, it will decrease, and then it will increase again. Okay, so we have that information here. Now, how might we go about solving this question? So let's say we have something like this, right? Let's say we have this algorithm here. Let's say we have this array over here. Okay, so we have this array over here, and actually maybe let me do a larger array. So maybe we have 7, 8, 9, and then 1, 2, 3, 4, 5, 6. Let's say we have something like this, right? So if we do binary search, we'll have left, mid, and then right. Okay, and now where's the pivot on this side? In this array, where's the pivot? Well, the pivot is right over here, right? The pivot is this one over here. So you can think of this as we go up, we go down, and then we go up, but we never cross the peak, right? We never cross this 9. So basically, all of the elements on this side must be less than all of the elements here. So we already illustrated that when we did this analysis here. And if you want to know more about that, just watch the last video that we did. But basically, what do we have, right? So let's say our target element is maybe this 4 over here, okay? So this might be like our target element. Alternatively, maybe our target element is over here. It can also be this. Our target element can also be the peak. So let's maybe consider these cases. Okay, so we already argued here that there will always be one half that is entirely increasing, right? So maybe why don't we just go ahead and we try to find the half that is entirely increasing. Okay, how can we do that? Well, I can just compare mid with the right-hand side element, right? Because if the right-hand side element is greater than mid, if it's greater than mid, then I know for a fact that this is entirely increasing. It has to be. We can't have a scenario where we go up and then we go down and then we go up and it's actually greater. It's greater than the initial element. Like, we can't have that. We already illustrated here that if we have a dip anywhere, if initially our array was like this and we have a dip anywhere, then whenever we increase our array, all of the items will be less than, it will be less than where we initially started off at, right? It will be less than this point and also be less than this point. So after the dip, it will always be less than the location that we originally started off at. You can kind of see that here, right? So here, if we have 5, we go all the way to 9, and then we go down, and then we increase. All of these items here are basically less than all of the items over here. So what can I conclude from that? Well, I can conclude that if mid is less than the right-hand side, if it's less than the right-hand side, then this has to be increasing, strictly increasing. The dip cannot exist here. Okay, so maybe let's go ahead and start off with that. So how can we start off? Well, we'll have a left and right pointers. Be length of nums minus 1. Here we'll do it while left is less than or equal to right. Why less than or equal to? Well, because whenever we want to find an index, right, and like we can find it and we want to return from inside of the binary search, then we can do it here. If you don't want to find the index, maybe you want to find a value or something that, you know, you're not passed in, like a minimum, find a maximum, then you would use something like this. But if we have something to find and we find it, then we can use less than or equal to. So let's maybe go ahead and do that. First of all, I'll find my midpoint. And then I'll check if nums at mid is equal to target, then I can just return mid, right? So this is why I'm using something like this. Now, if we go through all of this, but we actually can't find anything here, then this means that we can't actually find the target in the array. So we'll return minus 1. Okay, so now let's consider the scenario where we find the strictly increasing path, right? So the strictly increasing. So what we can do if nums at mid, if this is strictly less than nums at r, then we know that the right-hand side is strictly increasing, right? The right-hand side is strictly increasing. Otherwise, we know that the left-hand side is strictly increasing. And so if the left-hand side is strictly increasing, then the pivot must be on the right-hand side. So we know those two pieces of information. Okay, so let's assume here that the right-hand side is strictly increasing. And let's say I want to find the target 4. Well, how can I do that? How do I even know like 4 is part of this array, right? How do I know 4 might be part of this? We can just check, right? I can check. What can I check? If 4 is to be part of this array, which is strictly increasing by my assumption over here, then what I must have is I must have nums at mid. This must be less than my target, and my target must be less than or equal to the nums at r, right? My target, in order for it to lie in here, which is strictly increasing, it must satisfy this equation here. Now, if it does satisfy this equation, then what do I know? Well, I know that my search area can now be this. It can be the right-hand side. We're going to exclude mid because we already tested mid here, but basically my search area can now be the right-hand side here. So I would do left-hand side is equal to mid plus 1. If this fails, then we know that our search area must be on the left-hand side, right? Even though like this is strictly increasing, that's all fine. But if I can't find my target in a scenario like this, right? Like let's suppose target is 8 over here. Well, this condition fails. So I know my target must be on the left-hand side. Okay, so we have that. Now, what is the else case? So in this case, we checked that the right-hand side was strictly increasing. But what about the other case? What about the case where the left-hand side is strictly increasing? So what if we have something like this? What if we had something like, let's see, maybe 5, 6, 7, 8. And here we will have something like 9 and maybe 1, 2, 3, 4. Let's say we had something like this. Mid is over here. So clearly the right-hand side is not strictly increasing. We can see that because the 9 is greater than the 4. And let's say I want my target over here. Well, what can I check? So how do I make sure that my target is on the left-hand side? Well, I can easily check, right? I can check if nums at L, if this is either less than or equal to my target, and my target here is less than the midpoint, which is nums at mid. If this is the case, then it has to be on the left-hand side because this is strictly increasing. So I can do my right-hand side pointer becomes mid minus 1. So now we're just searching here. And if this is not the case, maybe my target is like this 2 over here. Maybe my target is this 2 over here. So if this case above fails, then I know that my search area must be right here. And again, we can skip mid because we already handled mid. In this case, my left-hand side becomes mid plus 1. And so this will be all of the scenarios. So now let me go ahead and run the code here. See that it passes. So it does. Let me go ahead and submit. And we can see we arrive at the solution. So this is the O of log n type solution, and the space is actually constant here. Now, what is the key takeaway we took from here? Well, the key takeaway we took is that if we have an array which is initially sorted, but then we introduce some sort of pivot somewhere else, then there has to be two halves that are entirely sorted. And if we try to find the target element in these half, for example, if I try to find it in this half, but it doesn't exist, then it's guaranteed to exist in this half, right? Regardless of whether this is like dipped or not, regardless of whether or not this has the pivot or not. But basically, that's the approach that we took here. Okay? Thanks for watching.